Hello and welcome to our first lesson in logarithms. It's going to be straight out of chapter 7. Logarithms is not actually going to start off with any calculus. I just want to review a few of the things you should remember from analysis to make sure that we're all on the same page. So basic definition of a logarithm is to say log base c of a equals b. Basically the idea that you want to be familiar with is that this is an alternative way to represent exponents. So instead of having this set up, where we have our log base c of a equals b, we can move things around a little bit. The base of the logarithm is going to be the base of the exponent version. A and b are going to switch sides, so now we have c raised to the b equals a. And that means the same thing as what was here. It's just an alternative notation for these exponents. Ideally, the purpose of logarithms is to get variables out of the exponent so we can use our regular algebra to solve them. Two comments. One is you should note that a is not allowed to be negative. It's important for the way this whole logarithm setup works. Is essentially you cannot find an exponent you can raise c up to suddenly change its sign. That's not possible. B can be negative, b can be a fraction, that's all okay. But a is not allowed to be negative. You should also note that with our common log, if there is no little number down in the bottom, we are assuming base 10. So here we get an example of a few of those common logs. This question basically is asking the same thing as, what power do I have to raise 10 up to make 100? Or 10 to what power equals 100? So this whole thing will evaluate to 2. Same argument here, I'm asking myself the question, what power do I have to raise 10 up to make 1 over 100? 1 over 100 you might think about as 10 to the negative 2, and now I have my answer. So this logarithm of 1 over 10 equals negative 2. It actually evaluates to the number. Here we see a couple more examples. The trick here is if you hit a logarithm statement that you don't know how to do, switch it to an exponent format. You've been doing exponents longer. So the logic here would be 2 to the third equals x. So x ends up being 8. Same argument here, I get 3, the base to the far side, equals the close side. 9 plus 4 is going to be 13. Here we get our laws of logarithms. Similar to our laws of exponents, it basically just says if you have two things multiplied together inside the log, you can add them together outside the log. Add the two logs together. Division, again, similar to exponent laws, dividing inside the log is subtracting the two logarithms. This one's pure common sense, but as we've seen, mathematicians don't accept common sense. So if you have log base b of m equals log base b of n, that will only work if and only if n and m are equivalent. If they're the same thing to start with, the logs still work. These last two are the ones we're most likely to use, honestly. And this first one says that if you have an exponent inside the logarithm, that can move out front to be a k in front of the logarithm for any real number k. So any exponent inside the log can come out front. Note that this does not work if you have log of x cubed. That's not what this is referring to. It's referring to log of x cubed. Then that becomes 3 log of x. Now if you want a justification for why that works, it actually is dependent on this first law. Our last rule that we want to know about is that if you have a log base b of b to the, they just cancel each other out and make x. Now our argument here is quite simple. If you have log base 2 of 8, this is saying, if I want to rewrite that as 2 cubed, log base 2 is asking the question, what power do I have to raise 2 up to make 2 cubed? What power I have to raise 2 up to make 2 cubed is just 3. So this log base 2 and this base 2 just cross each other out, and your answer is 3. Same goes if we go the other way around. If we say 2 raised up to the log base 2 of 3, log base 2 of 3 is the power I have to raise 2 up to make 3. Well, I'm going to raise 2 up to that power. That is 3. So these two guys just cross each other out, and you're left with 3. So what might that all look like? Here we have a log base 2 of x plus log base 2 of 3. I can't just cross the logs out because of this plus sign. This plus sign is blocking me from doing that. But I can use my log law that says that adding two logs is the same thing as multiplying their insides. So that can become 3x. Now both sides have a log base 2, so that's gone. And I get x squared equals 3x. You might be tempted to divide by x, but what we really want to do is subtract the 3x over and then get our two answers. Now note, x is allowed to be 0. It's not allowed to be negative, but it is allowed to be 0. It's allowed to be 0. It's basically just saying, what power do you have? Oh, whoa, halt. I just lied. It's not allowed to be 0 either. If this was log base 2 of 0, you're asking yourself, what power do I have to raise 2 up to make 0? There's no power I can raise 2 up to suddenly make it 0. That's not going to work. So this a value, I mentioned before, it's not allowed to be negative. It's not allowed to be 0 either. It's got to be a positive number. So this is an extraneous solution, and 3 is my only answer. All right, a problem like this is really just algebra to be able to set it all up. The trick is I want both sides to have the same base. If I can force both sides to have the same base, then suddenly life will be a little bit easier. So we've got our 2x. 2 to the 3 to the 3, you multiply those exponents and get 9. 4 doesn't look like the same base, but remember that's 2 squared. So this can become 2 to the 2/3. The 9 and the 2/3 are going to end up adding. So what's that going to give us? 29/3, which means that x is 29/3. When every base in the problem is basically just a power of 2, not even a multiple of 2, that's not good enough. It's got to be a power of 2. Then you can just force everything to have a base of 2, and then life is easy. Here we see an example we might see pretty often in calculus, and that is our 3 raised to the log base 3. Because this is a 3 and this is a 3, they just cross each other out. And you get your 7x equals 42. On this problem, unlike 2 ago where I had those 2's, those 4's, and those 8's, 8 cannot be rewritten as a power of 3. So this is really just a dead end. I can't evaluate this one using common sense. When you hit a dead end exponent problem, it's a good idea to think about logs. If I rearrange this problem, I can say log base 3 of 8 equals x. Log base 3 of 8 is actually a numerical value. Now, it should be noted that my calculator cannot evaluate log base 3 of 8. It does not have a log base 3 key. So I have two options. I could either go back to the original problem and take a log of both sides. The benefit of this is that it's the common log, 10, and therefore I do have that in my calculator. A log is a mathematical operation, just like square rooting. I can take that of both sides. This x comes out front of the log 3, based off my log laws. And then I can divide by log 3. This is more complicated than my other answer, but this I can actually evaluate in my calculator. If on my calculator I go to my log key, which is the word log for me right next to the 7, I can hit log 8, close my parenthesis, divide it by log 3. Optionally, I can close this last parenthesis or not. It doesn't really matter. I need to make sure I close that parenthesis on 8. Otherwise, the calculator thinks that this log 3 is inside of the first logarithm. Thinks about it, and it spits out 1.89. Alternatively, if you remember a little bit of analysis, you might recall that there's such a thing called the change of base formula. The change of base formula says that if I've got this base 3 and I don't want it, I can sneak a line into the problem and make that log 8 over log 3. And then I get to the exact same spot I was just there. The big benefit of this is that now again, my common log can be found on my calculator. My log base 3 cannot be found on my calculator. Maybe if you have a TI-89, you can do it on yours, but I can't do it on mine. All right, so in this problem, again, I see 3 logarithms. I would love for them to all have the same base to be able to continue. Square root of 3 and 9 actually can be converted to each other. That's possible. But with this log base 10, it's really just not going to happen. So I'd walk away from this problem. Pictures of what a log graph looks like and what I won't mention E yet, but what a log base graph looks like are going to be a little bit important. It's a good idea just to, when trying to graph something you're not 100% sure of, if you can't grab a calculator, pick a couple of control numbers to kind of think about it a little bit. When x is 1, I'm asking the question, what power do I have to raise 10 up to make 1? And that's going to give me 0. So I know that's one point on my graph. When x is 2, maybe not a good choice. When x is 10, I'm asking myself the question, what power do I have to raise 10 up to make 10? And that's the first power. So as you can see, this graph's going to level off quite a bit. I could also go the opposite direction, and I could make x 1/10, and then y is going to be -1, because 10 raised to the -1 power is 1/10. So I'm getting myself a little bit of an idea. As I go closer to 0, this number is going to get more negative, and as x gets really big, y is going to gradually get bigger. So it's going to go over a little bit like that. My domain is going to be up to, but not including 0, out to infinity. And my range looks like it's going down forever and up forever, although the up is very slow to be all real. All right, so E in the natural log. The natural log is this ln statement here. ln is essentially the same argument as log base E. E is Euler's constant. It's a very important number, much like pi, where it has a symbol that denotes it. It pops up all over the place in nature, whether you're trying to look at the number of ridges in a pine cone or the swirl inside of a conic shell or conch shell. These things pop up all over the place. So it has a name, just like pi does. E is on your calculator. If you want just plain old E, it's the second division. If you want e to be able to give it an exponent, you hit second ln. So to evaluate this problem, I have two arguments. I can either use my definition of logarithms and basically think about it as log base e of 4 equals 2x. Or if you prefer, I can take ln of both sides. ln and e just cancel each other out, and I get 2x equals ln of 4. And x is going to be ln of 4 divided by 2. Now that doesn't necessarily look the same as this side, but if you realize if I just divide by 2, log base e is ln, so they are the same thing. I could grab my calculator, take ln of 4, get a decimal, and then divide it by 2. Depending on which strategy you liked better in the last problem might depend on how easy you think this question is. If you try and combine the logs, it gets pretty complicated. But if you say that ln of e is just gone, and that's 5, and then that's x, the problem gets really easy. Negative x is going to equal 7, x equals negative 7. Note, I'm not allowed to have a negative inside of a log, but I am allowed to have a negative exponent inside of a log. That's allowed. This last example is a little tough, and you really want to be a master of exponents to understand it. The logic here is that this plus sign up in the exponent is a little troublesome. We want to think about where adding exponents might be used. If you have an x squared times x cubed, you would add that together to say x to the 5th. That x to the 5th is you actually being really good at this stuff and not thinking about where it comes from anymore. That 5 comes from that 2 plus 3. So adding exponents is the same thing as occurs when the bases are multiplied. If these exponents are added, that means that it could have began as an e to the 1 times e to the 3 ln of 4 as a separate statement. If you don't believe me, try and take this step and condense it, and you'll realize that they are actually equivalent statements. E to the 1 is just e. That's no big deal. This e and ln, I would love to be able to cross them out, but this 3 is in my way. To make this 3 get out of my way, I can bring it into the problem as an exponent. So this actually becomes e to the ln of 4 cubed. The benefit of that is now my e and my ln can cross each other out, and I've got this 4 cubed times e. Hopefully logarithms make a little bit more sense now, and it probably would be a good idea to review this again if you're having trouble with the homework. Bye.